Hi, let's continue our discussion of control systems and how we model physical systems. In this video, we're going to look at pole zero plots, and we'll just look at what it means. We've already said that the input output characteristic of a transfer function of a physical system can be uh, can be represented mathematically by a transfer function, right? So you could have a transfer function as I have shown on the screen here. Now, the denominator of the transfer function has a special name to it, and we call it the characteristic equation. Okay, so in this case, the characteristic equation is this polynomial here, s square plus 3s plus 2. Now, the poles of a system are the roots of the characteristic equation or the denominator polynomial. Okay, so the poles of this transfer function or this system are the roots of this equation s square plus 3s plus 2. Now, one of the reasons why this is called poles is think about what happens when this polynomial becomes 0, right? So the root, what do we mean by the roots of this polynomial? They are the values of s for which this polynomial becomes 0. So when this polynomial becomes 0, what's the value of the transfer function? Now this is the denominator. So the transfer function actually becomes equal to 0. Sorry, the polynomial, the denominator becomes equal to 0, because of which the transfer function becomes equal to infinity. So the poles are the values where the transfer function becomes infinite, and the zeros are the values of s for which the transfer function becomes 0, and they are the roots of the numerator polynomial. Okay, so for any transfer function, by taking the roots of the denominator polynomial and by taking the roots of the numerator polynomial, you should be able to get the poles and the zeros of that particular system or of that particular transfer function. What we can do then, so for example here, the transfer function, the denominator can be factorized into these two terms, and so we can see that the poles are at s equal to minus 1 and s equal to minus 2, and the zeros are at s equal to minus 3. Now we can plot these poles and zeros in the s plane, right? So s has a real component to it, which is denoted by sigma, and it has got a imaginary component to it, which is denoted by j omega. So this is now these poles and zeros can be plotted on this s plane. So we have a pole at minus 1 and minus 2, and poles are denoted by a cross, and you have a 0 at minus 3, and a 0 is denoted by a round, a 0. Okay, and so in this s plane we have plotted the poles and zeros, and this kind of a plot is called the pole zero plot. Let's take an example and work this out for another example, just to help you see how we do that. So let's say we have a transfer function given by this equation, and I want to find out the I say, please plot the pole zero plot. Tell me where in the S plane the poles and zeros lie. So what do? We need to find out the roots of the denominator polynomial, and we need to find out the roots of the numerator polynomial. And you can easily see that the zero of this system is when s plus 2 becomes 0. So s plus 2 becomes 0 at s equal to minus 2. Similarly, you can find out the roots of the denominator polynomial, and they turn out to be this. So they turn out to be minus 3 plus j root 7 and minus 3 minus j root 7. Now we want to plot it in the s plane. So this is the s plane. So here is the real part of the s, and here's the imaginary part. So for example, if you want to plot the pole here, the real part is minus 3 and the imaginary part is plus root 7 and minus root 7, right? For the 0, the real part is minus 2 and the imaginary part is 0. We don't have an imaginary part here. So if we plot this, we can plot the poles like this, and we can plot the 0 here. So this is the pole 0 plot for the transfer function that we have.